This is it. This is our abrupt restart. We just talked about different atomic radii. Now what we're going to do is we're going to talk about ionic radii. So we're going to talk about cation and anion radius. Radiuses, radii. All right, go ahead. Okay, now let's think about the difference between different atoms. Well, as you move from the left-hand side of the periodic table to the right-hand side, well, you're adding more neutrons. You're adding more protons, so your nucleus is getting a little bit more positively charged. You're also adding more electrons. Now, when it comes to cations, well, keep in mind what a cation is. A cation is a positively charged ion, which means there are more protons than electrons. So if you think back to that effective nuclear charge, if you have, say, 11 protons and 10 electrons, well, that 10th electron is going to kind of feel more effective force or more force pulling it in because it doesn't have that 11th electron to kind of balance it out. And so whenever you talk about a cation compared to the parent ion, what you're going to see, as we see in the case of sodium, well, sodium has an electron configuration of 1s2, 2s2, 2p6, 3s1. The valence electrons are in the third shell, or n equals 3, so that outermost shell. Na plus, what does that electron configuration look like? Well, where have you lost that electron? Well, you've lost that electron in that 3s orbital. So the Na plus ion has a valence shell of 2. The outermost electrons, since it's lost that 1 electron in the 3s orbital, the outermost electrons are in the 2s and 2p orbitals. So we've got something looking like that. Now, cations are generally going to be smaller than, or cations are going to be smaller than the parent atom. Okay, now let's think about an anion. Well, an anion has an extra electron, so it's going to have an overall negative charge. If we look at something like oxygen, oxygen has an electron configuration of 1s2, 2s2, 2p4, okay? The oxide anion, well, that has 2 additional electrons. Where are those 2 additional electrons going to be found? Those 2 additional electrons are going to be added to that 2p orbital. So you're going to have an electron configuration of 1s2, 2s2, 2p6. Now the valence shell is the same, but think about those valence shells. Each one of these has a valence shell of 2, but the oxide anion has a valence shell of 2 with a total of 8 electrons compared to oxygen, which only has 6 electrons. Okay, so your anions are going to be larger than those parent atoms. Here's our example. We've got oxide, which is 1.26 angstroms, compared to oxygen, which is only 0.73 angstroms. The blue sphere, or the blue half sphere, represents the oxide anion. So an additional look at anions, well, we already talked about oxygen. It has 8 protons, 8 electrons. Oxide, 8 protons, 10 electrons. Now, with that, I think that it's worth my time to go ahead and draw what this actually looks like. So let's think about our electron configuration. That's 1s2, 2s2, 2p, that's 2p4. Okay, so I'm going to use a red dot to show my electrons. Okay, and I'm going to use let's say a purple circle or a purple dot to indicate my nucleus. Okay, so there's my nucleus, there's my first 2 electrons. Those first 2 electrons are in that 1s orbital, that first sphere. And I'm going to go ahead and I'm going to go ahead and make my circle there. Okay, now my next 2 electrons. And I want to go ahead and cross out my 1s2 orbital. My next electrons are in the 2s orbital. I'm writing those in orange. I'm going to try to make a circle for those. And now, well, sorry, that accounts for my 2s2 electrons. So this is all of this is happening in 3 dimensions. Now, my next orbitals, which I'm going to do in green. I'm going to go with an olive colored green. We've got, that's one lobe of a 2p orbital. There's one, consider that my 2p or my 2p sub y. Okay, now I've got my 2p sub x, and this is a little bit tough because I'm not really that good at drawing, but here's my 2p z. Okay, now I have a total of 4 electrons in my 4p orbital. So I could put one here in my, I'm going to go ahead and go back with my original scheme of a dot. So I've got 1 electron here in my p sub y. Okay, now I've got 1 in my p sub x. I've got 1 in my p sub z. Okay, so that's 3 of my electrons. My 4th electron is going to go into my p sub y. So I've got 2 electrons, 1 in each lobe of my p sub y. Okay, so that means, what do I have? I've got 2 spaces. I'm going to go ahead and highlight them. I'm just going to draw a circle. Well, no, not a circle. I just want to highlight them with yellow. Here's a space that I could comfortably put an electron, right? And, well, I do in order to form my oxide ion. Okay, so my electron configuration, I really wish that I could just copy and paste that, but I've got my 1s, I've got my 2s, and then I've got my y, x, z. Okay, so again, x, z, y, x, z. Okay, so I've got 10 electrons. Now all of these electrons, they're going to occupy as much space as possible because keep in mind, those electrons, they're going to repel one another. My oxide, my O2 minus ion, that guy right there is larger than the oxygen parent atom. Okay, so you see those same sorts of periodic trends, or those same sort of, differences between an anion and a cation. Here's some highlighted examples. And what's important to recognize about these examples is on the left-hand side of this figure, which I've put a box around in green. Well, let's look at those atoms. We've got lithium, sodium, potassium, rubidium. Well, those are all going to form cations very easily. Those are all metals. Now I'm going to use, oh, I lost my cursor. There we are. I'm going to use yellow to highlight the other side of this. Group 6 and 7. Those are my, those are my nonmetals. What do I know about my nonmetals? Generally, they like to take on an electron. They like to become reduced. So oxygen, as is highlighted right here, I'm going to highlight even further. Woo. Oxygen versus the oxide ion. That's 0.73 angstroms to 1.26 angstroms. Okay, so that's something to keep in mind. Now, what I really want, the last thing that I want to draw your attention to right here is this item right here. Funny, the term that is written out on the side here. An isoelectronic series. If you think back, or if you break this word out a little bit, iso, well, that means same. And then, I probably could have picked a different color there. I apologize for that. Electronic. Okay, so we're talking about electrons. So an isoelectronic series is atoms and ions with the same number of electrons. Now, I would like to highlight, let's go with all of these. Sodium, magnesium, aluminum, oxygen, fluorine, oxide and fluoride. Now, I don't have the periodic table in front of me exactly, but I'm going to look it up real quick on the internet while this is all going on. Okay, so oxygen has an atomic number of 8. So Oxygen has 8 protons, 8 electrons. The oxide, O2-, so ion, I'm just going to write the ion form of the oxide ion that forms from oxygen, has a total of 10 electrons, hence the -2 charge. Now fluorine. Fluorine has 9 electrons. Okay. Fluorine forms the fluoride ion, which has 10 electrons as well. So oxide and fluoride, so O2- and F-, those are atoms, those are ions that are in an an isoelectronic series. Now, if we think about sodium, Na. Na has an atomic number of 11. It has 11 electrons. Well, what does sodium like to do? Sodium likes to lose one of those electrons. Sodium likes to become oxidized, so it's left with 10 electrons. So Na+. Okay. Magnesium, I hope that you can see a trend here. Magnesium and aluminum are all, magnesium has 12 electrons. Aluminum has 13 electrons. Well, magnesium likes to form that 2+ ion, Mg2+, which is shown here. That 2+ ion has 10 electrons. Aluminum has, lo and behold, 10 electrons. And that's Al3+. So all of these 5 different ions, some are anions, some are cations, they all form what is known as an isoelectronic series. All right, well, that'll do it. I hope you have a wonderful afternoon. Sorry for the lengthy video here, but I'll see you later.